Thank you very much. Okay, really, yeah, very, very good. Okay, I'm just sincere with that we can meet next year. Okay, even you are when you are back, I'm not your course teacher, but we still can meet. Okay, I think you are really very good. Okay, so let's continue our study. Yeah, do you have any question? Just you can tell me, ask me directly. Okay, that's very, very good way we have interaction with each other. Okay, I got a response from you. I will be really, very happy for that. Okay, I start to record. So it's very important, you know, the difference between solid and fluid. We should know that for the solid, here is the displacement, U indicate the displacement. But for fluid, here U is actually the velocity, is the displacement per second, okay? Or we can see the gamma for fluid is the strain, shear strain, but for the fluid is shear strain rate, or we say shear strain per unit time. Okay, so that's really very, very important one. So let's continue viscosity. So we know what happened to the fluid viscosity when temperature increase or decrease. It depends on its solid, it depends on its liquid or gas, okay? When it's liquid, when the temperature decrease, the fluid viscosity increase, right? Because when the temperature decrease, the liquid molecules will be closer because they feel cold. They want to be closer to feel warm. Okay, so the closer, the larger attractive forces between molecules. So the viscosity, or we call the internal friction, will be larger. The liquid viscosity increase. However, if the temperature decrease or if it became cold for the gas molecules, they don't want to move. So the thermal movement of molecules will drop. So the moment transfer from the movement of molecules drop, so the fluid viscosity for gas will also decrease. Okay. And this is mu, the fluid viscosity. Okay, the values of viscosity are tabulated in handbooks and textbooks. You don't need to you don't need to do experiments by yourself. We just refer to the handbooks or textbooks to get to obtain the viscosity of most fluids. Okay, and here, because of the viscosity, just now we have the classification of fluid. We just have real fluid. All the fluids are viscous. Some are just the viscosity is very small, just like the gas compared to, just like the air compared to water. The viscosity of air, the air viscosity is very small. But no matter how small it is still viscous. Okay, right? So for the viscosity, if we consider the viscosity of fluid, we call the real fluid or viscous fluid. But sometimes, just as we said, if the viscosity is too small, just like the air, is too small, is small enough, sometimes we ignore the viscosity of the fluid. We call them ideal fluid. That means it's not real. They are ideal fluid, or we name them inviscid or frictionless fluid. I think this one just corresponds to what you have learned in theoretical mechanics. We consider the friction a lot, right? So just now I said for viscous fluid, we have very important no slip boundary condition. The viscous fluid will have the same velocity with the solid boundary it contact with. However, if we don't consider, we don't account for the viscosity, the fluid is inviscid or the fluid is frictionless, there will be no slip bundle condition. We call them sleeping bundle condition. It's very important. Sleeping bundle condition, that means we still have the tangential velocity, okay, for the fluid contact with the solid bundle. Except for not only this, we use viscosity, we also have the kinematic viscosity. New kinematic viscosity is actually defined as the dynamic viscosity divided by the density. It is divided by the density because the density can also vary from the fluids, just like for the fluid. For the dynamic viscosity, water is larger than the air. However, if we don't consider that, if we just want to, if we use kinematic viscosity, or the dynamic viscosity divided by the density, the kinematic viscosity of water will be smaller than the air. So when we estimate the fluid days, or when we estimate whether it's easy to deform of a fluid, we need to use the kinematic viscosity. Okay. Because the kinematic viscosity excludes the influence of fluid density and only keeps the parameter of motion. And the dimension of kinematic viscosity is here is meter square per second. Okay, you can check out. So viscosity, we know that we can call another movie. So another movie will say how to find out the viscosity. For us, we don't need to, but for the scientists, they need to find out the viscosity. So they have this calculative viscometer to determine the viscosity. Okay, the viscosity is not measured directly, but we just measure some characteristic with a known relationship to viscosity. This one you can watch the movie by yourself. Okay, I can send to you. Okay, so you can see what happened here. And say here, if we measure velocity profile for water in life, that can be fit with a polynomial. The velocity is a function of y, and is equal to minus 1.1 y to the power of qubit. And then calculate for the shear stress. Yeah, just now we know from Newton that tau, the shear stress, is equal to fluid viscosity by the spatial derivative of velocity, right? Here, u is v1, okay. And then you can find out tau. Where is its maximum? What is the value? Where is its maximum? When the shear stress reaching maximum, when this one, because here viscosity is a constant. Generally, we regard viscosity as constant. Okay, even it depends on the temperature, but generally speaking, for most at the same temperature, okay, we just regard the viscosity as constant. Okay, so we can find its maximum, right? Its maximum. If you want to find the maximum, you will need to have the maximum, the first derivative of the velocity. And this one, we can find out the second derivative is equal to 0, right? It will reach its maximum or minimum, right? And here is a velocity profile of air over a car roof. Just like here, if this is a car, sorry for my drawing. Okay, so the air just moving around the car. And then here, the velocity profile on roof. This is its velocity. And this height from roof surface. So when the head from move surface is 0, the velocity is 0, and then when the head from would increase to 60, the velocity to increase to its maximum. So can you tell me where is the region of maximum shear stress? This is a velocity profile. This is a head from surface. The velocity increase from 0 to its maximum. Why it's 0 to its maximum? We know this is because no slip boundary condition, right? The fluid contact with the woof will have the same velocity with the woof, so equal to 0, and then it increase. We will have the maximum shear stress. Tau is equal to mu du dy. So shear stress, which is maximum when du dy is maximum. Du dy is which one? The slope, right? So here, the shear stress will have its maximum. How about here? Tau equal to what? Tau equal to 0. Why? Because here, the velocity doesn't change with the distance or with change with the height from surface. Here, tau almost equal to 0. This one, we want to tell that the shear stress is not decided by the magnitude of the velocity. It's decided by the velocity gradient. It's divided by velocity spatial gradient, okay? So here, the velocity spatial gradient is actually the slope of the curve. So here, the tau is actually equal to 0. That means the friction force is almost equal to 0. There is almost no friction force, okay? But near the woof, the shear force is large, or the friction force is large, okay? So just now, you asked me a very good question. Now, viscosity is a constant a lot. Yeah, for some fluids, they are constants. We call them Newtonian fluids. But for some others, the viscosity is not constant. We call them non-Newtonian fluids. Okay, so here, just for example, we got this XY plot. This is deformation rate. This is shear stress tau. And if for the shear stress, if tau for Newtonian, tau is equal to mu du dy, and mu is a constant. Just like here, mu is a constant, we call Newtonian fluid. However, for those, they are not constant, we call them non-Newtonian fluid. We can watch this movie and to see what happened to non-Newtonian fluid. They are very interesting one. Pore arch, okay? You see, they keep deforming. They behave like fluid, right? They don't behave like a solid. For solid, they will not continuously deform. However, it's strange. For fluid, we said we can cut them into pieces. But here, if you use a spoon, just for 1 second, they just are apart from each other. They behave like a solid. So what happened then? Actually, this one is cornstarch, is non-Newtonian fluid, and moreover, cornstarch is non-Newtonian shear thinking fluid. What does it mean? Means the fluid becomes more viscous as the shearing rate is suddenly increased. Okay, that means the more viscosity, the larger the shear stress is. So here, because the rapid action of the spoon, the viscosity of the cornstarch increases suddenly. We know that if the viscosity increases, it behaves like a solid, right? So this is a non-Newtonian fluid. The viscosity is not constant. It changes with the shear stress. It varies with the shear stress. Here is shear thickening fluid. Some viscosity change also with time. Here we don't consider that. We don't consider viscosity change with time. Okay. And we got this shear thickening fluid. So we got a lot of application of shear thickening non-Newtonian fluid. Just like here, we got the application of shear thickening non-Newtonian fluid to minimize head and neck injury. Also, we got this liquid body armor. It's viscosity. So the more stress applied to it, the more resistance it gives to that stress. Fabrics with shear thickening fluids could possibly be used to fortify the resistance of Army garments and body armor against puncture and ballistic threats. Originally when we started working on this material, we thought this was going to be armor. Our thought was we were going to have Ziploc with soldier, and it would be nice and flexible when he's walking around. And it would hit that stuff, it would turn hard and repel the projectile. Experiments in ARL prove that shear thickening fluid on it. You can see the video? Oh, let's share with you. Okay, just wait a minute. I share with this video to you. Okay, yeah, it's quite interesting. Now you can see it. Okay. It's viscosity. So the more stress applied to it, the more resistance it gives to that stress. Fabrics with shear thickening fluids could possibly be used to fortify the resistance of Army garments and body armor against puncture and ballistic threats. Originally when we started working on this material, we thought this was going to be armor. We thought we were going to have Ziploc bags of that liquid on the soldier. It's flexible when he's walking around, but then if a power would come in, it would hit that stuff, it would turn hard. And experiments at ARL proved that shear thickening fluid on its own was not effective as an armor material. So then we kind of went back to the drawing board and said, okay, well, how do we make this more useful as an armor material? So we got this idea that we had to reinforce this with something that's a little bit stronger. Engineers looked at treating Kevlar, a well-known high-strength, lightweight component found in military and law enforcement ballistic vests. Tests show that 4 layers of conventional Kevlar are easily penetrated with minimal force. What I have here is 4 layers of the same fabric, but I've treated it with this fluid. And when I say I treated it, it's not like we take this and we spread it on the outside like icing or something like that. It's not an external coating. What we actually do is we dilute this with solvent. We'll dip the fabric in the solution, pull it out again, and then this stuff kind of soaks into all the little nooks and crannies between the fibers, between the yarns and the fabric. Pull off the ethanol, and this gets left behind. But what is different about it is its response to threats, things like puncturing threats. This same technology can be applied to gloves, police, and medical personnel when walking around, but then if a projectile would come in, it would hit. Okay, you got it? This is the application of shear thinning, okay? I think I need to share with you, okay? Just wait a minute. This is shear thinning fluid. You see, when you just apply force, the liquid just behaves like steels, okay? Because when you just apply stronger force, the fluid become more resistance to the force, okay? Because of its fluid viscosity increase, okay, with the shear force, okay? This is called shear thickening non-Newtonian fluid. You got a lot of interesting phenomena related to this shear thickening fluid. But can you list some shear thinning fluid? Shear thinning fluid? I mean, here we mean if the shear stress increase, the fluid viscosity decrease. Can you list one? Blood. Blood is shear thinning fluid, okay? Blood is also non-Newtonian fluid, and it is not only non-Newtonian, but also shear thinning fluid. That means when you apply force, the viscosity of the blood decrease. Yeah, toothpaste. Yeah, thank you very much. Yes, they are shear thinning and fluid, okay? Yeah, thank you. You can list more and you can find more interesting phenomenon about shear thinning fluid. But because for us it's just introduction, so we don't go deep into it. You only need to know this. For us, it's introduction about the fluid property. You know viscosity. Viscosity is to resist the deformation, right? Is to resist to the shear force, okay? Viscosity. The larger the viscosity, the more resistant to the shear force. Okay, just like water versus silicon fluid viscosity. The second thing you need to know is with the increase of temperature, the liquid and the viscosity of liquid decrease while the viscosity of gas increase. Okay, and the third thing is not only dynamic viscosity, we also have kinematic viscosity, which is equal to dynamic viscosity divided by density. And another thing you need to know is when the viscosity is equal to given as a constant, we call it Newtonian flow. Otherwise, we call them non-Newtonian flow. Okay, yeah, it's very interesting. You got a lot interesting phenomenon about the non-Newtonian fluid. Okay, you can check online by yourself. Okay, but we don't talk about anymore about Newtonian fluid, non-Newtonian fluid, because about non-Newtonian fluid there will be specific costs for non-Newtonian fluid. Okay. Except the viscosity, we have another important property for fluid, compressibility. Compressibility indicates how easily can the volume or the density of a given mass of the fluid be changed when there is a change in pressure. Or we say how compressible is a fluid. That means whether the volume change easily or just will keep unchanged. Okay. We introduce the Bach modulus of elasticity to indicate the measurements of fluid resistance to a uniform compression. And this is a definition, the Bach modulus. Oh, sorry. Here, you say the Bach modulus. Can you know the unit of the Bach modulus? This is a volume. Volume. Okay, this volume. What is the unit of the modulus? The unit of the modulus should have the same with the pressure, right? This pressure, the pressure difference, right? Because it cancel with each other, right? One thing. Why here is volume, here is density. Why we got a minus here? Why we got a minus here? Because when dP is larger than 0, dV should be smaller than 0. That's why we have the minus here, right? Because we want the Mach modulus of elasticity is always a positive value, okay? And also because mass conservation and the mass conservation, we know the mass equal to density times the volume. So that's why we can use the volume change or we can use the density change, okay? So this is a compressibility, okay? So accordingly, if the fluid is not easy to compress, or the modulus of the fluid is huge, we just regard it as incompressible, just like most liquids. The Bach Barker modulus is quite large, okay? It's 10 to the power of 9, okay? It's very huge, it's huge values, right? This we call the fluid as incompressible. That means when the pressure change, the volume or the density keep fixed, keep unchanged, okay? Okay, so definitely for incompressible flow, we have compressible flow. Compressible flow means when the pressure change and the volume easily change. You can think about this for air, for the gas. We know that when the pressure change, the volume of the gas will easily change, right? So gas generally can be compressible, regarded as compressible. For the liquid, we consider it as incompressible. But for hydraulics, we talk about incompressible or compressible. We mean when the fluid moves, whether it's a fluid element change or not. Okay. So here you need to tell the difference. When we say the fluid is incompressible or not, we mean when the pressure change, whether it's fluid volume change easily or not. Okay, we say water is incompressible. Most liquid we treated as incompressible, air as compressible. But here in this course, we talk about incompressible or compressible actually means when the fluid is in motion, whether the fluid, the volume of the fluid element change a lot. Okay, so sometimes even for the air, we still regard it as incompressible fluid. Okay, because its density, the density change variation is quite small. Okay, so for this one, for compressible and incompressible, we will have very different performance. For example, we have this sound of speed. You know, sound of speed. When we talk about, when I speak, you can hear me. Why you can hear me? Because when I speak, the pressure near my mouth change, right? The pressure impulse propagate, and that's why you can hear me. Okay, and the speed of the pressure pulse propagate is named as sound of speed. And we know in air, sound of speed is 340 meter per second almost. And do you have this experience in daily life? When you speak, when you go swimming, when you speak underwater, the sound of speed is faster or smaller compared to you speak in air. Can you tell me? We know. Yeah, much faster because it's incompressible. Okay. Or we mean it's incompressible means if there is pressure impulse, it will propagate to everyone at 1 second. Everybody knows that there is pressure variation. Okay, that's incompressible. And one more thing I need to address here is most time we regard water as incompressible, right? But sometimes we need to consider the compressibility of water, just like water hammer. Later on, maybe we will talk about that. So most time we can regard water as incompressible, but sometimes we still need to consider its compressibility because no matter how small the variation of volume it is, but there is still variation. Sometimes we can ignore them, but sometimes we need to account for them. Okay. I got a very interesting video for you. Just you can take a look to have more idea about the fluid compressibility. Okay. Can you say it? Can you say it? So I should share with you, okay? I think I have recommended this course to you, right? This is online course. You can just, this is from MIT. It's called Classical Mechanics, okay? For this course is really very, very good. I just strongly recommend you to watch by yourself. It's a very good one. It includes what we have learned, thermometric mechanics and material mechanics and fluid mechanics cover not everything, but it's very good.
Going to change topics and talk to you about. All I have to do is take liquid.
No, sorry, I just want to show you.
Well, before we reach this to be vacuum, believe me, it already implodes. So the forces that we're dealing with are comparable to what Van Drebel was dealing with when he built his submarine. And so this can.
Sorry.
In order to cover the stage, of an atmosphere. Remember, 10 meters of water is one atmosphere pressure. First, to put myself in.
I want to show you.
Would you assist me with that?
Let me do this way. Okay, because I can't find it right now. Let me do this way. Let me describe this to you. We got two boxes. Okay, we got two boxes. One is full of water. The other is full of air. Okay, two boxes. One is full of water. The other one is full of air. And then this professor, this famous professor, he got a gun. He just shot the two boxes, and one is exploding. It's got hit, and one box exploded. The other one just kept quiet, and there is only two small holes left on the box. So can you tell me which one exploded? The one full of water or the one full of air? Which box will explode when it's hit by the gun? We shot it. Can you tell me? Can you try to tell me which one will explode? Do I need to describe to you again? Yeah, the air. Somebody said the air will explode. Are you sure it's air? Again, again we said there are two boxes. You got the gun, what got our gun to shoot them. And one box get exploded. You got a huge bomb. But the other box, when you shoot it, yeah, everything just can be quiet. Just we know we got the sound of bullet, but no exploding. And when we check it out, there got two holes, small holes. Which one? That's for sure the one full of water exploded. Why? Because the water is incompressible when there is a pressure pulse. When there is pressure change, it will propagate to everywhere at 1 second. We call that underwater, the sound of speed is much larger. It's almost 1,500 meters per second. Okay. I always give this example to students just like for incompressible flow, Just like if a guy, it just takes a knife to the classroom, and if it's incompressible flow, and he know this guy got a knife, he will say, oh, there's a guy got a knife, and everybody knows this, and everybody wrong, everybody is in panic, and the classroom is in chaos, right? Just like the box is in chaos. Everybody wants to go out of the classroom, go out of the box. The box is closed. Okay. However, if it's a classroom full of air students, and one air student found out that there is a guy is taking a knife, he knows that and tells another guy, but just from his face, you see nothing. Yes, you see nothing. Just keep quiet, keep just calm, and finally everybody knows that there is a guy just have a knife, and he go from this door, from front door to the back door, and then leave. Nothing happened. So you see, this is the difference for compressible and incompressible flow. Do you got it? I don't know whether I explain to you clearly because it's in English and we are not in person. Okay. So again, for incompressible and compressible, the big difference is for incompressible, the pressure pulse just propagate with a large speed, with a huge speed. But for the compressible flow, because it can just resist the compression to some extent, so the propagation of pressure pulse is much smaller. Okay, that's the difference. And in fluid statics, we will see the difference between the hydraulic lift. Okay, so this one we don't need to know. Okay, so for up now, for flow, we have the classification of the flow, which is according to whether to consider the viscosity. We have the invisible flow and the viscous flow. And for the viscous flow, if the viscosity is a constant, we name it Newtonian flow. And otherwise, it's non-Newtonian flow. And for flow can be classified into incompressible flow or compressible flow. For incompressible flow, we got it as the density of the fluid particle is constant. Okay, the density of the fluid particle is constant. Okay, and that means when the pressure change, the volume keeps fixed. Okay, so that's incompressible flow. Just like the water, we always regard it as incompressible. But for the water, sometimes we still need to consider its compressibility. Okay. For compressible flow, just like the air is compressible flow because pressure change is volume change a lot. Okay, but here in this course, because we talk about is compressible and incompressible, whether the fluid volume change when the fluid moving. So sometimes for air, we still can regard it as incompressible. For example, we say we have this Mach value. This one is Mach number is divided by the velocity divided by the sound of speed. If smaller than 0.3, we regard it as incompressible flow. Okay. And so if you study thermodynamics, also there is another very important property of fluid is expansivity. This one is to describe how the fluid volume change when the temperature change. Okay, so but if you here for us, because we don't do a lot of topics related to temperature change, so for us expansivity, just we don't talk about a lot. Okay, just know this. Okay, here we have a very interesting phenomenon, surface tension phenomenon. Surface tension in everyday life. Okay, you say this water beating on a leaf is almost spheric, right? I say it's almost spheric. Okay, not strictly spheric because it's on the Earth because of the gravity force, right? If it's in space, if there's no gravity force and the water beating will be spheric. Okay, this is the flower, and the flower just surprisingly it does not sink. Instead, it just floating. This is because of surface tension, and also here we got the coin. You see the coin, we know that it's absolutely much denser than the water. But however, the coin just did not think. Yeah, it just also float. And this one definitely is not because buoyancy force. If because the buoyancy force definitely it will sink to the ground, right? And this is related to surface tension force. And also we have this video, we can see you can do these experiments by yourself. You will see this according to the, if we just do the FBD, if we draw the force body analysis, you will see the buoyancy force, the weight, and it's supposed to sink, but however, it's floating because of surface tension force. So what's surface tension force? Here, definition. Surface tension is due to the asymmetrical cohesive forces acting on the molecules of a space surface. The interface between a liquid and a gas, and is a macroscopic manifestation of molecular force. What does that mean? Here, look inside the molecular distribution, and inside the fluid, okay, inside fluid, the molecules have the attraction forces by other molecules, okay, and it's get balanced because it got the forces by any direction, okay, it got balanced, okay. However, for the molecules of the free surface, okay, the free surface, we mean that this is an interface. We got the density variation between this liquid and gas, right? We got the property in continuity. And so the molecular got the force, molecular force by the inner molecular, and the force by the air molecule is quite small. So definitely the molecular of the free surface will have the resultant force go inward, right? According to the FBD for this molecule, for example, or for this molecule, and it got molecular force from the inner molecules of the liquids, but it got also the force by attracted force by gas molecules, but the gas molecules just the force is like relatively small, so it got unbalanced. The force will go inward, so that's why the free surface or the interface or called the membrane will just this will have the tensile force will result in the interface to shrink or to have this hyperesthetic skin. Okay, this is the reason of the free surface tension force. Or this is the surface tension force is actually the result of the asymmetrical cohesive forces acting on the molecules of the free surface. Okay, And for the surface tension, and we use sigma to increase surface tension force, and this surface tension force by length, okay, per length, okay. Surface tension force is actually force per length. So its unit is Newton per second, okay. So wherever there is a density discontinuity between a liquid and another liquid, gas, or solid, or we say if there is density discontinuity, there will be surface tension force. And we got another interesting phenomenon related to surface tension force, and we will talk about it next week. Okay, see you next week. Okay, that's all for today. Next week we will continue